Good morning, dear students. Today's topic is 4-bit binary parallel adder. So it means we have to design a logic circuit which can add parallelly two numbers which are 4 bits each. So let us see this nomenclature: 4-bit binary parallel adder. It means 4-bit numbers are there. There are two 4-bit numbers and these are binary in nature, and we have to add them parallelly. Okay, so we have to design a combinational circuit for this purpose. So let us see that we first assume that a number a is a3 a2 a1 a0 and a number b is b3 b2 b1 b0. Now since these two numbers are binary in nature, we can add them using full adders. Why using full adder? Why not half adder? Because these are there may be a possibility of a carry also, that on addition of a0 and b0 a carry may be generated. So it may be a third input for the next a1 and b1 addition. So there are 4 full adders required because these are 4 binary 4-bit numbers. So let us say talk about FA0. We have given the names FA0, FA1, FA2 and FA3 depending upon the positions at which these are placed. FA0 is the least significant bit adder, full adder, and we have named it FA0. Similarly, we have named FA1 corresponding to a full adder which is responsible for addition of A1 and B1. Similarly, we have given a name FA2 and FA3. Now, to start with, let us say the least significant bit is to be added first. It means A0 and B0 are to be added. So since we know that full adder has 3 inputs and 2 outputs, so the 3 inputs are A0, B0 and there is a carry input which is initially 0. Initially there is no carry, so we have assumed it 0, and we can see that C in is grounded, so it is 0 which is given to the C0. So there is no input carry initially, which is C0, and we have added A0 and B0 and in the full adder 0. So the outputs should be S0 and C1. So S0 we can get as the output here, and C1 is a carry which is generated from the least significant bit addition, and this carry will become an input for full adder 1. So FA1 we have given the name to the next full adder where there are 3 inputs required. These 3 inputs will be A1 and B1 along with this C1. C1 is the carry output of the FA0 full adder, and this will become the carry input for FA1 full adder. So the 3 inputs are complete: A1, B1 and C1. So for this full adder, S1 is the sum output and C2 is the carry output. So these are the 2 outputs of FA1. Similarly, the C2 which is the carry output of FA1 will become the input for the FA2 input carry, and it already has A2 and B2 as 2 inputs. So C2 becomes the third input, and these 3 inputs when sent to full adder 2 will give 2 outputs S2 and C3. So these 2 outputs we can take and for our purpose, and this C3 is sent to full adder 3. It means the output carry of FA2 will become the input carry of FA3, and there are 2 inputs already, A3 and B3, which are the most significant bits of the 2 numbers. and then finally C4 becomes the output carry, and S3 becomes the sum from this addition of A3, B3 and C3. Now this C4 is also the final carry output, because this is the last stage of addition. All the 4 bits addition is completed here, and C out becomes, it means the C4 becomes a C out, and C out is the final output carry of this 4-bit addition, binary parallel addition. So it means we can get S3, S2, S1, S0 as the sum, and C out as carry, final carry. So what does it mean? That if there are two 4-bit numbers, one number is A3, A2, A1, A0, another number is B3, B2, B1, B0, and if we sum these two numbers, there may be a 5th binary number as a result. So the 4-bit number S3, S2, S2, S1, S0 will be the output along with C out, and C out is called the carry. So what we can say, that we have added A3, A2, A1, A0 and B3, B2, B1, B0, and the result becomes C out S3, S2, S1, S0. So the result may be a 5-bit number. If C out, since all these are C out, S3, S2, S1, S0 are either 0 or 1s, so C out may be 0 or 1. When C out is 0, we will say there is no final carry output, and when C out is 1, we'll say that there is a output carry generated. So this is very much possible. If we add two 4-bit numbers, we can get an output carry. So you can add any two 4-bit numbers. You can take a few examples, and you can ensure whether C out is 0 or 1. So in some cases you will find C out 0, in other cases you will find C out 1, and nothing else other than 0 or 1. So I think it is clear that if C out is 0, there is no carry generated, and if C out is 1, we can say that the carry is generated. Now this we have designed using 4 full adders, and this we can design and implement in laboratory also. We require 4 full adder ICs. We have inbuilt ICs of full adders, so those 4 full adder ICs can be utilized, and the connections can be performed in this manner. Also we have a ready-made IC for this 4-bit binary parallel adder, which is 7483. So this we have shown a logic symbol of IC 7483. What does it do? It requires 8 inputs, and it will give us 5 outputs. In fact, 9 inputs are required. How? There is C in as a carry input, which is generally 0, because initially there is no carry. In the process of addition, there may be a carry generated, and that is the final output carry. It will give C out. Intermediate carries are now of no importance, although inside this IC the connection is like this. This is the connection diagram inside this IC, and also we know that full adder is made from basic gates. So inside this full adder, each full adder, basic gates are involved. For each full adder, we know that the sum is the XORing of the 3 inputs, and also we know the carry output, which is XY plus YZ plus ZX. So let us say FA3. So the what is inbuilt in FA3? X XOR Y XOR C XOR Z. X XOR Y XOR Z. Let us say these are the 3 inputs. So the sum will be this, and carry will be XY plus YZ plus ZX. So 2 XOR gates are required for sum. Okay, and 3 and 2 OR. This we all have studied in detail in class. So this is just I am telling that inside these also there are basic gates, but 7483 IC is a portable IC which is directly can give the sum of 4 bits in binary added parallelly. So these 4 bit numbers can be added directly with the help of 7483 IC, where let us say there is an input X which is X3, X2, X1, X0, 4 bits, and similarly there is an input Y which is Y3, Y2, Y1, Y0 bits, and there is an input carry C in which is 0. So we can get the output in the form of the sum S3, S2, S1, S0 and the output C out. This X3, X2, X1, X0 is same as B3, B2, B1, B0, and Y3, Y2, Y1, Y0 is maybe same as A3, A2, A1, A0. Okay, so this 8 inputs along with an input carry can lead to 4 outputs S3, S2, S1, S0 and an output carry C out. So what does it mean? That when X3, X2, X1, X0 is added with Y3, Y2, Y1, Y0, it will lead to C out S3, S2, S1, S0. That is 2 4-bit numbers may be added to provide a 5-bit output number, 5-bit number, which is the result of this. Carry out may be 0. If it is 0, then we will get no carry. Output will be also 4 bits. But if we get C output as 1, then there is a carry generated from this addition. Now this IC 7483 can also be cascaded with another similar ICs to add a bigger number, a more number of bits. Okay, let us see this. That this is the cascading of two 7483 ICs. What does it do? Let us say there is one IC 7483 in the least significant position, and here 2 4-bit numbers are added, and the result is generated as S3, S2, S1, S0. Carry out, which is generated from 7483 IC in the right hand side, least significant place, is provided to the another IC in cascade, which is also 7483, and here the bits from X4 to X7 and Y4 to Y7 are added. It means we have two 8-bit numbers, and these are being added with the help of two 7483 ICs. So it means this 4-bit binary parallel adder can also help in addition of 8-bit binary parallel adder. This 7483 IC is a 4-bit binary parallel adder, but we can add 8 bits, 12 bits, 16 bits and so on by cascading these ICs numbers. IC number 7483, if we cascade two 7483 ICs like this, 8-bit number can be added. Similarly, 4 7483 ICs can be cascaded to provide 16-bit number addition, and so on. So this is clear from this figure that cascading is done like this, where output of 7483 IC at the right hand side is having the C out as the intermediate carry generated, and which is the input carry for the next 7483 IC in cascade, and then X4 to X7 becomes the 4 bits inputs, and Y4 to Y7 becomes the 4-bit input of the next input, and the sum from S4 to S7 may be generated, and there is a final output carry which is C out in the left hand side 7483 IC, or we can say most significant placed IC. So here we can say that from X0 to X7 8-bit number, and Y0 to Y7 another 8-bit number, these both numbers are added to get the result S0 to S7 8-bit result, along with any carry if generated C out. It means two 8-bit numbers X0 to X7 and Y0 to Y7 may lead to the result of a 9-bit number, which is S0 to S7 and C out. It means most significant place C out, and then S7, S6, S5, S4, S3, S2, S1, S0. This may become a 9-bit number. If C out is 0, then the result is also 8-bit, but if C out is 1, the result becomes 9-bit number. So hope you have understood clearly. If any doubt, you can ask through WhatsApp. Thank you.